Hello everyone, welcome back. We last time talked about what a robot is and how we define a robot, right? Let's just quickly recap through that and then we will dive into the world of sensors. So in our fancy schmancy definition of a robot, we said that hey, a robot has three building blocks. It's an intelligent agent which is tasked with doing certain set of things in the world. So it involves a perception module where it can sense the world and sort of use that to get a gauge of what is around the robot. Then it uses this perception modality to make a plan of what needs to be done next. We call this planning or decision making. And then once the plan is made, we basically say, hey, we are going to change certain things about actuation modalities, which we can, for example, changing the speed of a motor to be able to accomplish the task. In the example in the bottom here, you see that the aerial robot or a quadrotor or a drone is present in a forest-like scenario. It can sense the world and it can get a distance map or a gauge of distances of how far something is. And it needs to go from point A to point B without hitting any of the obstacles, right? And that's what the perception modality is. In the planning modality, we say, hey, what's the path we need to take so that we actually don't hit any obstacles. And in the control modality, we say how do we change our motor speeds to be able to follow this path along, right? But the first building block of a robot involves around sensing, right? And this brings us to the world of sensors. Before we dive in, we need to define what a sensor is, right? We perceive a lot of things in the world, and most of the sensors are on our face. So I just want you to take a second and ponder upon what is a sensor. How would you define one? If you were to explain this to an 80-year-old child, what a sensor is, what would that be? The vague definition of a sensor is that it lets us understand what is going around us. In a more formal sense, it's a device which responds or detects or measures a physical property and it indicates it to us, right? For example, a physical property could be like air pressure, a physical property could be temperature, it could be smell, any of these kind of things, right? Remember that a sensor is defined around a physical entity because we said that, hey, the robot has to respond to the things in the environment, for which we need to be able to understand what the environment is doing and what is the state of my agent or my robot in this environment, and which involves these physical properties and physical quantities, right? Okay, so in other words, vaguely put, it's essentially saying how we perceive the world, right? I want you to understand that sensing and perception are often swapped in place, but they're not literally the same thing, right? As a roboticist or a computer vision person, you really want to understand the fundamental difference here. Sensor is merely getting a gauge of this physical property, but perception is cognitively one level higher where you understand what this sensor is, right? Getting a distance might be a sensor, but using this distance to physically build a three-dimensional map around you to be able to understand what is obstacle free path is perception, right? Remember, they're very related, and sensing leads to perception. Often these modules are combined into a robot, but they do not mean physically the same thing. Okay, just to quickly recap, a sensor is a device which measures a physical property, and it essentially gives us information about what this physical property is entailing, right? And on one step higher than that cognitively is perception. You take these raw sensor values like a voltage or a current or a number, and then you make sense out of what this actually physically means for me, right? And be able to understand what I can do with this sensory information. Okay, let's move forward and let me ask you a simple question. We have seen sensors all around us and we possess a lot of these sensors. What are the most common type of sensors you might have seen or you might think of when I ask you this question? A small hint is that focus on the sensors we have, and we can sort of classify them and box them into these kind of sensors, right? Most of you might be thinking about your eyes or your ears or your mouth and things like that. And you're absolutely correct when you think about things like this. And we will basically like box these into kind of sensors which we will use to develop sensors for our robots itself. Let's start simple. First is vision-based sensors, which are akin to what we see in the world, like through our eyes. Then we have touch-based sensors. It's something similar to our skin, wherein we interact with the button on our phone, or we tap that like button for this YouTube video, or we type the comments in this video. That's the touch sensor. Then you're hearing this video through your phone speakers, and it goes through your ears, and then like the ear drum vibrates, and that's a sound sensor. Again, remember that we hear an audible range of 20 to 20 kilohertz, but sound can be something much higher than that, called ultrasound, which bats do, and it can be something much lower, right? And then we have taste, where we taste delicious food through our tongue because they react to certain chemical compounds. And last but not the least, we have smell, right? Smell is basically a sensor which reacts to these like compounds in the air molecules, and we get an idea of smell, right? We can smell the delicious food, or we can smell the stench of garbage, which tells us, hey, keep away from that. So these are all the senses we have evolved over millions of years, so that we can be safe, we can be able to do the duties we want to do, we can find a mate, and all these kinds of things, right? And most of the time we use all these senses. There are human beings where some of the senses are a little impaired compared to others, but a combination of these sensors is what lets us achieve what we want to do in day-to-day life. Awesome. Now that we have learnt about sensors, let me ask you a very fundamental, simple question. What kind of a sensor enables you to know how much your knee is rotated? Let me make this into a thought experiment. Imagine you are in a dark room. To help you sort of like envision this, if you're sitting in a room or you're outside with lights on, close your eyes, and you can still sort of like sense how your body is oriented. You can still sort of sense how much your knee is moving, how much your hands are moving. And if I ask you to move your hands to touch your nose, you can probably do it. If I ask you to take a step front or back or left or right, you can really do this well, right? Remember that we have impaired most of our sensors. We have impaired vision. We have impaired mostly touch, because we cannot touch anything around us. Sound is still active. Of course, we are not really tasting anything. We can still sort of sense the stuff around us, but I don't think that's helping us much with understanding how my knee is rotated, right? I want you to take a second to think about what is the sensor that's actually helping me stay put, stay level, be able to move my hands in a particular way so that I can like accurately touch my nose. Take a second and pause the video to take a guess. The answer is that it's none of the things we just talked about, right? Which we have another amazing super sense. It's like the Spider-Man Spidey sense or the sixth sense. This is called internal perception or proprioception, right? All the other things were called exteroception because it's reacting to something external. Proprioception is knowledge and sensing of the self of the body itself, right? Generally, it resides in your muscle fibers. You have this thing called muscle spindle and a Golgi tendon organ. So as you move your body parts like hands or legs or your stomach, basically the muscles flex and stretch and like compress. This affects internally like how this muscle, the muscle spindle and Golgi tendon are in tension, right? This tension lets you understand how much the particular joint has moved, and that's what really lets you understand how we are physically moving in three-dimensional space. And we utilize this all the time to understand what to do, right? And to answer the question I asked you before, how do you know you're standing upright, right? This helped you understand how we are touching our nose. But to stand upright, we have an internal measurement in our ear canal, which lets us know what is the direction of gravitational force that lets us stand upright. Okay, so again, these all come into proprioception, and the equivalent of what our ear canal stuff is in robots is called an inertial measurement unit, and the equivalent of that for the muscle spindle stuff is called a motor encoder, which lets the motor know how much it's turning. Okay, now what I will do is, in the next few slides we will play a game wherein we will look at a robot and we will look at a video of this robot, and we will basically ask a few questions about it, because whenever you see a robot in the real world, I want you to be able to like look at a video of the robot or look at a task a robot is doing and be able to like decipher, hey, what were the scientists thinking when they designed this robot, and what is the software that's actually internally happening inside. Okay, we'll start with our most famous example. This is a Boston Dynamics Atlas humanoid robot. Again, this is the previous generation of the robot, which has been replaced with a newer one. We've seen these robots do amazing stuff, like this parkour robot. So let me play this video and then we will go forward. We just saw the Boston Dynamics Atlas robot do amazing parkour. It did some amazing stuff. It jumped around obstacles, it moved around obstacles in a very fine and refined manner. So to just sort of probe you and hint you towards what the robot was seeing, this is a visualization developed by the Boston Dynamics team. It's sort of showing what's going on inside the head of the robot and what it's sensing and perceiving and the kind of stuff it's doing inside. Okay. So let's ask the question, what sensors does the Atlas robot have? Pause the video, look at the images, do not cheat, please do not search on the web. Try to guess what the sensors are on this robot based on the functionality you just saw. The Atlas has a stream of sensors, lets you do these amazing tasks. If you carefully observe the head, it basically has a LiDAR on it, which lets it sense the three-dimensional scene using throwing out laser light and obtaining the reflection of how far something is. It has encoders like we talked about, like on every single joint. It has temperature sensors on every single joint, which lets it know if a motor has overheated. This is sort of analogous to when you work out in a gym or you like run for a long time, your body like and joint starts hurting. That's lactic acid building up in these muscles, which are telling you, hey, like you need to stop or else it's gonna be really bad for your muscles, right? Then we see that like the robot also has a bunch of cameras on it, so to be able to like recognize objects and know what to step on and things like that. It has like pressure and force sensors on the foot. It has a bunch of other stream of sensors for knowing three-dimensional stuff, doing obstacle avoidance and like things like that. Okay, again, this is like a very small example of the kind of stuff the robot has. So let's go forward and ask the next question. What does the perception or the vision stack do in this case on an Atlas humanoid robot to be able to do parkour like this? I would say again, pause the video, take a second, ponder upon it, and then come back. So to be able to like step on these different kinds of scenarios, the Atlas needs to know what is a flat surface, what is a surface it can step on that it won't crumble. So it needs to sort of recognize, okay, hey, like this is a material which is good, I can step on it, nothing will happen. It needs to be able to plan its future steps, as you're seeing in this video with the green little footsteps. Like where do I place my foot so that I don't fall over, but I also don't knock over the obstacles that are in my way. It has to be able to like understand from its foot that like how much pressure am I putting, is it gonna like collapse the wall and things like that. Okay, so let's do this one more time. So here we have a PRG Husky robot, which is basically a modified Parrot Bebop quadrotor with its own sensing engine. Let's look at the video again and then we will come back and ask a couple of questions. again, to ask the question, what are the sensors the Husky has? Right? You saw that the robot was essentially moving around the scene, and it is trying to detect this unknown shaped gap, and it flew through it. Right? Some of you might think, hey, I'm just going to put a depth sensor on this robot. It's going to be super easy. I'm going to detect where the gap is and move on in life. Well, your answer is correct. I don't disagree with that answer at all. But the idea is that we wanted to do this in a minimal way. So the question we asked in this research paper was like, hey, what's the minimum number of things we need to do this, right? And if you observe on the left side, the PRG Husky has a big camera in the front. It definitely has encoders for all these motors. It has a down-facing sonar to know the height, and it also has a down-facing camera to know how it's moving in XY space. Okay, these are all the sensors that's on the robot. Good. So what is the perception of the vision stack have now that I've told you that, hey, we are not really sensing depth directly, right? So what the PRG Husky is doing is it's physically moving in space, and it's capturing images as it goes along at about 30 times a second. And it's matching the current image to the next image to know like how much each of these pixels have moved. And that sort of gives us a gauge of where the gap is. And if you're wondering why does that make sense? If you have a hole in a wall and you move around the scene, the hole itself is going to move a lot and the thing in the back is going to move very differently, right? And this is called parallax. To sort of do this experiment for yourself, put your thumb out, close one eye, and then open that eye and close the next eye, and you'll see that the hand moves in front of you, which is very differently from the background and behind you, right? And this is called parallax. And again, we do this with two eyes, but we wanted to do the same thing with a single camera so that the robot is essentially moving around and faking this second camera, right? So that's how we get the vision stack for this obstacle avoidance task. Okay, let's continue our game. This is a Boston Dynamics Spot Mini, which is like a dog-like quadruped robot. And again, it can do a multitude of tasks. So let's look at the video and see what it does. Let's continue and play this game. Again, the question is like, what are the sensors the Spot has? It's very similar to what we saw in the Atlas or the PRG Husky. It has a bunch of cameras in the front. It has a bunch of encoders on each of its joints. It has a bunch of sensors on the bottom to know the height. And again, it can also have ultrasound sensors for obstacle avoidance, right? In this image, you don't see the Spot with the arm, but in the video you did. So again, each of these arms also have similar kind of sensors, which we just talked about. So we saw this like Spot robot do some amazing stuff. It basically opened the door. It like held the door ajar with its body and sort of moved it. And that needs a lot of perception and vision stack, right? So as you would be expecting, it knows how to recognize the door. It knows how to recognize the knob on the door. It knows how to move the arm in a particular way to be able to like rotate the door handle by how much force so that it doesn't like rip the knob off. And like how it can like, it knows the concept that the door is a hinged entity so that it can put its body there to hold it open and things like that. Again, These are cognitively really complicated tasks, but can be sort of clubbed into the perception pipeline as well. Okay, so let's go a little more advanced. So let's now look at a Tesla Model S. This is on the right side, I'm going to play a video now, which is going to be the Tesla like autonomously driving and detecting a wide variety of stuff to be able to do self-driving on its own. Okay. So if I ask the question, what sensors do the car have? Some of you who know about Tesla might give the correct answer. If not, your guess would be that it has a stream of sensors like a LiDAR, like a bunch of cameras and a bunch of radars. And you would not be wrong in saying that, okay? But Tesla as a company decided that they only want to use cameras. So they actually forgot the only other sensor they had on the car, which is ultrasound sensors, right? So the Tesla Model S in this particular case has about 13 cameras all around, which it uses to get an understanding of the world and basically sense the world around it. Okay. So let's ask the question, what does the perception or the vision stack here do, right? As you see on the screen here, it's detecting all these like road signs, it's detecting these road lane markings, it's detecting where the road is drivable, it is detecting like other things like, is it raining, is it like is there construction and all these kind of things. It's detecting every other vehicle and obstacle on the road so that it doesn't hit them, and it's basically also estimating how the car is moving so it can stay centered in the lane and all this kind of stuff, apart from a multitude of other things. Okay, it's of course detecting the speed and all these things as well. Let's continue playing this game. And in this particular case, we have a PRG Labrador 500 Alpha, which is a big robot, and it's going to do a bunch of tasks. Okay, let's look at the video. Here again, focus on only the parts where you don't see the bird. The bird is just there for inspiration of the cool stuff nature can do, but just focus on the drone footage from this video. You just saw the PRG Labrador Alpha do some very cool stuff, right? You saw it do like dodging of dynamic obstacles where we were throwing toys at the robot. You saw it navigate through like a cluttered forest in the blue scenario, and you saw it like navigate through gaps which are unknown shaped. So what do you think are the sensors on the Labrador? You might think that, hey, like we can use a depth camera to do all this stuff, and you wouldn't be wrong, apart from the other height sensors and all that stuff. In this particular research work, we basically again focused only on doing this with a single monocular camera, like you saw with the previous example where we were like moving the robot to detect the gap. It is a similar concept, right? So given that information, what do you think is the perception stack? You might say that, hey, like you're doing the exact same thing from before, which is looking at parallax, and you would be 100% correct. But the way we do this is a little different. We basically detect like the matching features between the two images, like we discussed. This term is called optical flow. But instead of computing the full optical flow and looking at that, because it's computationally really expensive, we actually found a very nifty way, or a parsimonious way, that uses a lot less resources, about a factor of magnitude less resources. We call it the uncertainty, or the aleatoric uncertainty in this optical flow. Essentially, what it's telling you is that, hey, I want to estimate this matching or optical flow, but that thing is really expensive. Instead, can you just tell me where this matching is likely to fail, right? And just knowing that information, it will mostly fail the boundaries of objects, which is what we are really concerned with, right? And that helped us do this stuff. And this work got us to the cover of Science Robotics Journal, which is one of the top journals in the field of robotics. Coming up with these kind of approaches to do perception with very minimal compute is a whole new class of perception engines called minimal perception, which I do a lot of research on. And it's very exciting because we can mimic what these honeybees can do with exceptional amount of accuracy, but with very minimal compute, which our robots are yet to match today. And I believe this is the future where we have to go towards, wherein we build very efficient models rather than throwing a lot of compute and a lot of power into solving these like small tasks, right? And it's very cool. And in the future videos, we will dedicate a whole series on optical flow. Optical flow is a very cool concept which almost every biological being uses, and it's a very, very cool thing. Okay. Again, so after this video, you should be able to answer what a robot is from last time, and what are the common kind of robotic sensors. You should know how a robot would know if its knee has moved, and you might be able to really spot the different robotics components of a robot in the wild and be like, aha, I know how that can work, right? And I hope I've inspired or piqued you with some curiosity about the robots around you, and hopefully you can go look at them in a little more detail and sort of speculate on what is going on in the perception engine and what it actually is sensing. And in some sense, you can dream in the world of a robot or through robot's eyes. Take care. See you guys next time. Bye bye.